Ladies and gentlemen, boys and girls, welcome to another episode of Transparent Physics. In this lesson, we are going to continue the dynamic series with an introductory discussion about friction. In this lesson, we're going to define what friction is and note a common misconception about the role of friction. We're going to talk about the three factors that determine how much friction you'll have in any given scenario. And we'll compare specifically within one of those three factors, static and kinetic friction. I would say in general, friction as an everyday English word tends to have a bit of a negative connotation in it. You don't hear a conversation that talks about the friction between two people as a good thing. And in terms of a physics sense, if people were asked to define what friction was, odds are it would circle somewhere around the idea of friction slowing things down. And friction can slow things down, but it is responsible for a lot more than that. And looking at it a little more deeply, a lot of the things that you take for granted every day would be impossible without friction. To tease that idea out a little further, imagine a world where everything was slippery, not slimy, just slippery, super smooth. And it would be an almost unrecognizable world to the one that we live in. Walking would be impossible. Imagine trying to walk on an icy surface all day long. Car tires wouldn't help you at all. When you get into your car, assuming it hadn't slid to the bottom of the hill, there would be no traction between you and the road. Objects would have to be designed very differently because it would be very hard to hold anything that didn't have a handle associated with it. If you were cold, you couldn't rely on the old trick of rubbing your hands together to generate some warmth. And perhaps the heaviest hit of all, tug of war would cease to exist as a recreational activity at picnics. So truly an unrecognizable world, and one that I would agree none of us would want to live in. A recurring theme in transparent physics is the idea that everyday words have sometimes very specific and different meanings when used in a physics context, and friction is no different. Friction in physics specifically refers to a force that arises to oppose slippage between two surfaces. And slippage is simply the act of slipping when two surfaces slide with respect to each other. And in this context, friction can serve a lot of different roles. It could completely prevent the slippage in the first place, or it might be acting to oppose slippage, which is already occurring. Let's see some examples of that. So let's take a look at a friction sampler. First of all, what most people think of when they think of friction is friction bringing an object to rest. So you can see this person was in motion to start, and then he slides to a stop as a result of friction between him and the ice. The next one, friction prevents this person from moving. Off camera, I believe there's some sort of like tractor or something like that. So you could argue that friction between him and the ground keeps him from sliding forward. And another friction you could look at is the friction between him and the rope. And if it wasn't for that friction, he would not be able to stop the object off camera from moving as well. And finally, we have a conveyor belt, and these boxes are actually moving because of friction between the box and the belt. So three very different sort of applications of friction. The top one shows an object in motion that's being brought to rest. The second one shows an object that's being prevented from moving, and the bottom one shows friction actually encouraging motion to occur. Okay, before we get into the conceptual nitty-gritty, time for a quick sip of tea. Thank you to friction for me being able to hold my cup of tea. So the focus for the rest of this video is going to be talking about the three S's of friction. I actually debated on whether or not it should be the 5 S's of friction, because technically there's 2 more S's in terms of the two surfaces themselves. Don't forget, friction exists between two surfaces, but generally in terms of application, that means a surface like a wall or a floor or a road or a ramp or something like that and then there's an object that's touching that surface. But that object itself has a surface, so two surfaces are touching each other. But we don't include those in the 3 S's overall. The 3 S's of friction officially are the squish. How hard are the two surfaces pushed together? The second S is the swoosh. How easily do the two surfaces slide across each other? And the final S is the shift. Do the surfaces change position with respect to each other? We're going to talk about each of these in more detail moving forward. All right, starting with the squish. The harder you press an object against a surface, the more the surface presses it back on the object. That's Newton's third law. Now, this force is often equal to the object's weight in introductory physics, but it's not always equal to the object's weight. So you got to be careful. You got to look if there's other forces that have vertical components that are factoring in as well. This force that presses back up on an object, that keeps the object from moving through that surface, whether it's you sitting on a chair or an apple sitting on a table or a car sitting on a road, all those forces can be characterized as normal forces. Now, while it is perfectly normal to not pass through a surface that you are pressing against, that's not actually the reason it's called the normal force. It's called the normal force because mathematically, normal is a word that means perpendicular. And when we look at the normal force, it is always oriented perpendicular to the surface. And again, depending on your introductory physics course, this may not be a very big deal. A lot of the times, you're just going to be dealing with a horizontal surface, like a car on a road or an apple on a table or something like that. But if your course deals with ramps, and sometimes more advanced problems actually deal with like objects being pressed against walls. So if your surface is oriented some way besides horizontal, the normal force is always oriented perpendicular to the surface, regardless of the orientation of the surface itself. Now the argument is that the bigger the normal force, the bigger the squish between the two surfaces, the larger the frictional force is as well. And you can demonstrate this very easily to yourself. Just put your hand on the table or desk that's nearby you, glide your hand across the table, and then repeat the same motion, but this time press down onto the table while you're doing it. You'll see that the amount of friction does increase notably. And there's lots of real-world applications for this. If you have a rear-wheel drive car, maybe not as popular as they used to be. Some trucks are. In the winter, you'll put heavy stuff in the back of your truck, which will help your tires grip a little bit more because the back of your car is pressing down harder on the road surface. And just in general, anytime you see the word traction, that's an equivalent term to friction. And if a race car, the sort of the fin that goes across the back trunk of the car, that's designed so when the air flows over it, the air pushes the back of the car down, and that also increases the traction of the car the faster the car goes. On to the next S, swoosh, which is the coefficient of friction, and some surfaces just slide more easily over other surfaces. The Teflon pan gained popularity because food would slide off the surface and not stick to it. Many a gag in movies and TV shows has been the result of a banana peel placed appropriately on the floor, and that is a slippery substance to put your foot on. Other surfaces don't slide over each other very easily at all. If you have two glass plates and you put them together, if you try to slide one glass plate over another glass plate, it's actually pretty hard to do. And any sort of athletic shoes, I'm thinking like basketball shoes, but I'm sure really anything comes into play there. You don't want those sliding. All right? You don't want to pull like a Tom Cruise risky business move on the basketball court. When you put your foot down, you want to be able to exert a force on the floor and go in the direction you want to go. Now, we have a way to quantify that relationship as to how rough or smooth, how easily these surfaces move across each other through the term coefficient of friction. When we're using the idea of the slip, aka the coefficient of friction, in a calculation, we need to ask ourselves whether or not the surfaces are slipping with respect to each other. And let me explain that in a little more detail. In the first scenario, we have static friction. The word static means unchanging. And if you have static friction, that means the position of the object is not changing with respect to the surface it presses against. A way to imagine this is, say, if you take a can of spray paint and you just sort of spray it down the object onto the surface. If static friction is in play, the line that you painted on the object and the line that you painted on the surface are going to stay connected because there's not slippage with respect to those two surfaces. On the other hand, we have kinetic friction. Kinetic is a word that means movement. And if we have kinetic friction in action, that means the surfaces are slipping with respect to each other. Maybe the object is sliding over the surface. And if we go back to the spray paint example, and I had sprayed painted a line down the object onto the surface, if kinetic friction was in play, those two lines of paint would separate from each other because the two surfaces are no longer fixed in position with respect to each other, they're slipping. And this is an important consideration to you as an introductory physics student, because you're going to have to look at the scenario and ask yourself, is this a static friction scenario or a kinetic friction scenario? Because when you're dealing with the coefficient of friction, you're going to find that it changes mathematically depending on which of the two scenarios you're working with. And you need to make that decision to make sure you get the right answer. Let's look at an example of how that actually comes into play, and with a quick visit to the lab.
Okay, so here we are in the lab. I have a 5 kilogram mass on top of a wooden block. The frictional interaction we're interested in is the wooden block versus the lab table. And I can slowly increase the amount of force I'm pulling on the scale with. And this is static friction right now because the block is not sliding with respect to the table. I can exert more force, up past 12 now. 13, 14, 15. All right, so I got around 15 max, and you can see now that it's sliding, the amount of friction I'm getting is less than that. So we have entered the realm of kinetic friction now, and kinetic friction can't give you as much as static friction can at its maximum value.
Okay, what we just saw happen in the lab is represented mathematically by this relationship. I mean, this is not an exact plot of the data, but this is a general diagram that you'll see a lot when physics teachers talk about friction. And what this represents is the idea of we're applying a force to an object that's represented on the x-axis, and then the amount of friction in response to that is on the y-axis. So when I was pulling on the scale, what you saw is before the object started to move, the amount of friction went up and up and up and up and up and up, and at some point the surfaces could not stay fixed with respect to each other. Basically, on a molecular level, you sort of got the nooks and crannies of the wood in the nooks and crannies of the table surface, but there's an increasing stress as we apply force on them, and at some point the two surfaces are going to break with respect to each other, and then there's going to be a start of motion. The idea is, in theory it shouldn't matter how fast the object's moving from that point onward. The amount of friction has dropped and is supposed to remain relatively constant, but again, you saw in the video, it bounces around some. Now, this relationship between these two scenarios is critical to understanding friction. And the boundary that we really always need to focus on is this idea of slippage, which is represented in the chart by the point where the friction drops notably. It's at this point that the wood block starts sliding with respect to the lab table. and that divides this graph into two sections. The section on the left is the static friction scenario. And the static friction is interesting because it's not necessarily a fixed value. And when we go to calculate static friction, really the calculation is going to tell us the maximum amount of static friction that we could get for the scenario. But static friction can be less. If you just gently push on a desk, you're not going to get the full amount of potential static friction acting back on you. It will only resist enough to keep the object from moving. Once the object starts to slip, we're in the kinetic friction range. And kinetic friction, again, in theory, is constant once the object starts to move. You saw from the video, though, it bounces around some, but generally in introductory physics, we just say, hey, once the object starts to move, you're in the realm of kinetic friction, and that's going to be a constant. But the key thing is that the maximum amount of kinetic friction that you can ever get is always less than the maximum amount of static friction. Now, the idea of static and kinetic friction is like a conceptual minefield. There's so many places that you could get tripped up on. I'll point out two sort of common misconceptions I've seen over the years in my own classroom. First of all, when I'm talking about static friction, kids are usually pretty quick to get the idea that the surfaces aren't slipping with respect to each other. But then the assumption seems to be in a lot of minds that, well, if there's no slippage, that means the object's not moving. And that's not necessarily true. We saw that conveyor belt a couple minutes ago, and that is static friction between the box and the conveyor belt. It is because of friction that the object's moving. Another scenario might be, maybe there's a worker and she puts her tool chest in the back of her truck, not pushed up against the back, just sort of placed in the center of the truck bed. And she gets in and drives off. If that toolbox stays in a fixed position, it accelerates with the car because of static friction. So static friction, even though the idea means not changing, it's the position of the object with respect to the surface that isn't changing. But if the friction helps the object move with the surface, sometimes people can confuse and think that's not necessarily static friction anymore. But again, static friction does not mean the object's not moving. It means the object's not slipping. And in the same regards, whenever we're in a kinetic friction scenario, a lot of people assume that, well, kinetic friction means the object needs to be moving as a result of it. And a classic, maybe counterpoint to that is the old pull the tablecloth out from under the dinnerware scenario. And kinetic friction could actually mean the object's at rest. If you yank the tablecloth fast enough, the idea is that the friction between the tablecloth and, say, the plate is a kinetic friction because the surfaces are sliding with respect to each other. I put a little asterisk there because technically anytime you do that trick, the plates are going to move a little bit, but you can do it fast enough so there's almost no time for the object to accelerate at all. All right, an idea or two to wrap up with. I mean, friction is a good thing to talk about because we understand friction just from our everyday lives, but there are a lot of things that go into figuring out how much friction you're going to have. We introduced the idea of the normal force, which is the squish. We introduced the coefficient of friction, which is the swoosh, and we talked about whether or not the object is slipping or not, and that's the shift. You put all those together, and we're going to be able in the next lesson to actually start mathematically calculating friction and showing how it can come into play, and we'll be able to address increasingly more realistic scenarios with the addition of friction in the mix. All right, we're going to do a quick friction check. What I want you to do is pick up your cell phones or move your computer mouse or run your hand across the touchpad. Maybe just move the cursor to the like button, give it a click, make sure it's still working. Maybe type a couple words in the comment field about any questions or comments you have what I said in this video. And just to make sure it's still working, find where that subscribe button is and click that too, just to make sure friction's still doing what it's supposed to do. One of the great things about physics is you can take sort of an everyday phenomenon like friction, look under the hood and find out there's so much more going on than you thought. So I appreciate you learning a little bit more about friction with me, and hopefully I made things a little clearer for you on this lesson of transparent physics.